Welcome back, everyone. I'm Supergirl Charlie. Today we are taking a deep dive into large language models or LLMs. Whether you're a junior in the field or just a person interested in new technologies, you're welcome to my channel. So please make sure to subscribe and like this video and share with your friends because this is going to be the first part about large language models. So in first part, we'll explore how LLMs, large language models, are actually designed, how they work under the hood, from tokenization and embeddings to transformers and self-attention, pre-training and next token prediction. In the second part, we'll look what happens after that, like fine-tuning, RLHF, context windows, and memory hallucinations, like how these windows work with memory, and hallucinations, inference, limitations that we have, and real world applications. So let's get started and uncover the technology behind today's most powerful AI systems. Yep, I prepared some slides for you. If anything is new to you, like some words that you don't understand, you can ask ChatGPT, Gemini, or Claude, whatever you use, whatever agent you're into, or just Google it because I try to explain everything in easiest way, but there can be still some technical words that are like for you, like what is it? Then you can just Google it and look through it. I do my best to make it easier for you, but yeah, still. Let's uncover this technology, how it works under the hood, and bear with me. You have probably asked many questions to ChatGPT, depending on your expertise or just interest, to Claude, Gemini. Some of us interacted with GitHub Copilot. These systems can answer questions, write text, generate code, summarize documents, and even help people brainstorm ideas. But how can one model perform so many different tasks itself? Like in this presentation, we will look under the hood, we will explore how everything connects, how language becomes numbers, and how transformers process context, how models work with enormous datasets and learn from these enormous datasets, and how they generate responses one token at a time. The key idea to remember is that LLMs are not traditional databases containing ready-made answers. No, they are trained systems that predict what text is most likely to come next. What are LLMs? What are large language models? An LLM is an artificial intelligence model trained on extremely large amount of text. The word large can describe several things, like the amount of training data, the number of internal parameters, and the computational resources required to train and run the model itself. So during training, model processes books, articles, code, conversations, whatever we give to it, and many other forms of written language. It learns statistical patterns such as grammar, sentence structure, associations between concepts, and common ways people communicate. What are patterns? Later on, I will explain with actual examples. So all of this allows it to generate human-like responses, summarize information, translate languages, write code, and also it helps to perform many other language-based tasks. However, an LLM does not understand the word like word, our word in exactly the same way human can understand the word. Like it produces responses by calculating probable sequences of tokens based on patterns learned during training. We know different terminologies, and some people confuse each of them with like ML is AI, AI isn't ML. So I will explain now. Deep learning, AI, machine learning, and large language models. What is their differentiation? Like these terms are related, but they do not mean the same thing. Artificial intelligence is the broadest category, and it refers to machines performing tasks that normally require human intelligence, such as understanding language, recognizing images, making decisions. We still have problems with this because it doesn't do it perfectly yet. We don't have AGI yet. What is AGI? You can learn about it from my previous video that is in the same playlist this video is in. And this playlist, as I said, will be for both beginners and people who are in tech. So, machine learning. As we understood, okay, artificial intelligence is broadest category. Then we have machine learning. Machine learning is branch of artificial intelligence. Instead of programming every rule manually, we give system a data and allow it learn patterns. I want to talk about what is a pattern. For example, you know that whenever, for example, you ask your husband or your son or daughter to do some household thing, they say, yes, I will do it, and usually it gets prolonged by 3 hours. When you stop saying it and just don't talk to them, then they do it eventually. It can be a pattern of human behavior, of behavior of your son or daughter, or for example, there can be people who, whenever they see a dog or a cute pet, they start talking in a squishy voice, and then they go back to normal speaking when they speak to person. That is also a pattern. Like deep learning is a branch of machine learning that uses neural networks for with many layers, and these networks can learn very complex patterns like from large data sets. Then we can talk about large language models that are deep learning systems designed specifically to work with language. A simple way to imagine hierarchy is this. AI, artificial intelligence, is the largest circle. Machine learning sits inside AI, deep learning sits inside machine learning, and LLMs are one important type of deep learning model. So let's go to tokenization. Don't be scared of this word, I will explain it in a bit. Before an LLM can process any language, the text must be converted into smaller units called tokens. A token can be a complete word, part of word, punctuation, or even an individual character. So the exact result depends on the tokenizer used by the model. A common word such as book may be represented as one token. Less common words such as unhappiness might be divided into several small tokens. Each token is then mapped to a numerical identifier from the model's vocabulary. For you to understand it better, like imagine your neighbor and you live in different flats. Each flat has their number, yes, 7, 8, 9, etc. So each token has numerical identifier, like you have your flat identifier, or your flat has its number, your neighbor's flat has its number. So each token has its mapped numerical identifier. This means the model never directly sees words in the way we do. It receives sequences of numbers representing those words and word pieces. Tokenization matters because context limits, API costs, and processing time are usually measured in tokens rather than in words. This is very important for business. Imagine that any token is money for the business. Yeah. The next step is to convert each token into an embedding. An embedding is a vector, which is a long list of numerical values. These values represent characteristics and relationships learned by the model. Tokens with related meanings, yes, often appear closer to each other, closer together in this mathematical vector space. For example, let's bring an example like king, queen, man, woman, crown, may have related vector patterns. Embeddings allow the model to work with meaning mathematically, and it is very important to understand that these relationships are learned from patterns in training data. No human manually defines the exact numerical meaning of each word. The transformer is the core architecture behind most modern LLMs. It was introduced in 2017 research paper. Attention is all you need. Earlier, language models often produced like words sequentially. Sequential order we understand, yes, like 1, 2, 3, 4, and they're sitting beside each other by sequence, one after another. This made training slower and made it harder to capture relationships between words that were far apart. So they could be far apart, but they could be closely connected, yes? But this didn't work well. Transformers changed this by allowing many tokens to be processed in parallel. Transformer contains repeated layers of attention mechanisms, feed-forward neural networks, and residual connections, and normalization operations. All these are hard to understand, but believe me, if you read more about this, I won't go into details now, but in advanced part, when I start an advanced course, advanced playlist, I'll talk more about this. So each layer gradually creates a richer representation of the input. So after passing through many transformer layers, the model itself has a contextual representation that can be used to predict next token that comes after that token. Self-attention allows every token to examine the other tokens in the context and determine which ones are most relevant. That's why it is called self-attention, that because it examines all the tokens in context, like deep dives into itself, and determines which ones are most relevant to each other. And consider for example, let's consider a sentence, yes? The cat climbed into the sofa because it was tired. So now to understand what it refers to, the model needs to connect the word with cat. It word, I mean. Yeah? It climbed. So it should understand that it is a cat. Self-attention helps create this relationship, and each token produces 3 vectors called query, key, and value. What is key and value? For non-tech people, like, for example, if someone like asks, what is your name? My name is Maria, for example, or Charlie in tech. So it will be like name, dot, dot. This is a JSON format, for example. Name, Mariam. Nickname, Charlie, or pseudonym. Key will be here the name, and value will be Mariam. So each token produces 3 vectors: query, what we need, what we ask for, yes, key, and value. Query is the question. Imagine it's same as a question, asking a person a question and they answer, oh, name, key is this. The query represents what the token is looking for. The key represents what information a token may contain. The value contains the information that can be passed forward. So the model compares queries between each other and keys as well to calculate like attention scores, its scores, each of them. And these scores actually determine how strongly each token should focus on the others. Modern transformers use multiple attention heads, like so that different types of relationships can be learned simultaneously. We have to talk about positional encoding here. Transformers process tokens in parallel, as we understood, so they need another mechanism to understand word order. Without positional information, the sentences the dog chased the cat and the cat chased the dog would contain like same tokens, even though their meanings are completely different. Positional encoding adds information about where each token appears in the sentence. The original transformer used sine and cosine functions to create unique numerical patterns for each position. Later in the advanced course, I will talk more about cosine similarity that we use in some models, for likeliness. And here comes that cosine similarity. Modern models that we use may use other approaches, including like relative positional encodings, and may also use rotary positional embeddings that are about which I will also talk later, not in this course. The exact method can vary. What we choose can vary depending on what we want to do, but the goal actually is the same: to preserve information about order and distance between tokens. But what is useful in which situation can be completely different from technical side. So token embeddings and positional information are combined before being processed by the transformer layers. Pre-training. My favorite part of this all is pre-training. Like, pre-training is the stage where the model learns general language patterns from an enormous dataset. The dataset may contain books, websites, source code, like articles, and academical materials, archive materials, many other types of texts. And by the way, imagine by saying enormous dataset, imagine like dataset where there are 1 million rows, or 1 million users with 8 million rows of information. So it can happen. So during pre-training, the model repeatedly tries to predict missing or upcoming tokens. When its prediction is wrong, an optimization algorithm slightly adjusts the model's internal parameters. The model itself learns throughout the process, and this process happens billions and trillions of times. Over time, the model learns grammar, writing styles, associations between concepts, common facts, and coding patterns itself, and also can learn some problem-solving behaviors by itself, based on the information it grasped. The model is not simply memorizing every sentence, it is learning a compressed statistical representation of patterns found across the whole training data. Pre-training is extremely expensive and may require large clusters of specialized computing hardware that big businesses can afford. Next, token prediction is a very interesting concept. It's a central task behind most generative large language models. Suppose the input is like cat set on the and cat set on the, and it doesn't have continuation, for example, ... The model calculates probabilities for many possible next tokens. For example, mat, sofa, chair, they can receive high probabilities, yes? All of these words can be possible. But some of these words may have more predictability. For example, it is more probable that cat sat on a mat because pets have their own mats, yes? Or their own beds. Then a chair, because some owners don't allow their pets to sit on the sofa or chair. But the next with the probability comes exactly the chair, sofa. If cat is tired, even if cat is tired, there could be that possibility. First is map, second possibility can be like sofa, because chair is more of a dry place. Not soft can be chair, and the last probability can be floor. So it will depend and vary. The model selects one token based on their probabilities. That selected token can be added to the context, and the model repeats the process. This creates autoregressive loop, and reading the existing tokens like that already are there. It will calculate possible next tokens and select one, append it, and repeat. A full paragraph is therefore generated one token at a time. The model does not plan the entire response before writing it. Each new token is influenced by the sequence that already exists there. Let's stop here. I know the information was a lot, so let's stop here because you already learned core part of the mechanism behind large language models and the AI. Supergirl Charlie in tech is here with you. So bear with me and wait for the second part, whoever liked this part. Perfect. Congratulations, you know how large language models work under the hood. At least you know the basic information how they work, and you can share it with your friends and relatives. After that, we will go on with the second part, which will come live in probably in the next week. In the second part, we will learn like how large language models are fine-tuned, controlled, used in practice, like how memory is managed, what are hallucinations, what limitations we have when we deal with AI models, large language models, and what are real-world applications. Of course, like I did in first part, I will bring examples from real life to make it easier for you to understand everything. Yeah, if you have any questions, just write in the comments. Yeah, make sure to ask them, because later on I'm going to cover more topics. Maybe when you ask a question, there'll be an idea for a new topic. Maybe I didn't imagine that some part of this is harder for you, and I may even create some shorts for you to understand a specific part of this mechanism. Not to lose information on second part too, please make sure to subscribe and like and share with your friends. Thank you very much. Bye bye and have a good day. Charlie is with you in your tech journey. Bye bye.